Welcome to everyone who's joined us today on this Friday evening. I see the numbers are climbing, and so I'm very excited. I am Dr. C Rathilal, a lecturer at the University of Johannesburg. And today I am here on behalf of NITheCS, the National Institute for Theoretical and Computational Sciences, and behalf of my own initiative, Absolute X, where we are going to be assisting you in preparing for upcoming exams. So as you would have seen from the poster that was shared when you registered, we have 2 lessons that are planned for the next 2 weeks. Today is the first lesson and next Friday will be the second. So in today's lesson, the aim here would be to help you prepare for topics that will be covered in Mathematics Paper 1. And in the subsequent lesson, in the lesson next week, we will then be helping you prepare for Mathematics Paper 2. Okay, so let's talk about Math Paper 1. But just one more thing before we continue, just some ground rules. So as you can see, you are now in a webinar platform. So for those of you joining us live, please note that we have a chat box and we have a Q&A that has been set up. I'd request the following, that you would use the chat box to just answer basic questions that I may ask you or leave comments, but you use the Q&A box to actually pose important questions that you would like me to answer or explain to you during the lesson. So remember, the chat box are for comments and the Q&A is for serious questions. All right, so I hope we all follow those rules. One more thing, please note that this session is being recorded and we will have this recording made available on the NITheCS YouTube channel. So we have lots of fantastic and fun things coming up. And all you'd have to do is subscribe to the channel so you're kept updated. All right, so let's talk Mathematics Paper 1. So in Mathematics Paper 1, specifically for Term 1 content, what are the things that you're going to be assessed on? So firstly, you're going to be assessed on concepts covering basic arithmetic, and this would include things like factorization of polynomial expressions. And this, of course, you've been dealing with since grade 10. So factorization is nothing new to you at this point in grade 12. In fact, I think you were learning how to pull out a common factor when you were in grade 8, right? But I stand to be corrected. So that's factorization. Then you would also be tested on inequalities, and simplification of expressions. Okay, so mathematical expressions, of course. The next bit that you would be tested on in the upcoming Paper 1 would be number patterns. And series. Okay, so what I am going to be focusing a lot more on today is point number 2. So just to get a feel for the crowd today, have you all covered number patterns already in your own particular classroom in school? You can just type in yes, you can type in a no. I just want to see your response. I'm going to be asking lots of yes or no questions and I want to get some feedback. So let's keep the feedback going, right? So let's try and be as interactive as possible on this webinar platform. So thank you for that resounding yes. Number patterns and series have already been covered. So what I'm going to do is I'm going to reinforce your knowledge and we're going to look at some exam type questions. All right, so let's do just that. All right, so thank you for that. So I can't keep on checking the chat box, but I will go back to it occasionally. All right, so when we're dealing with number patterns, in particular, you would have realized that there are 3 types that you would have covered already in school. So let's talk about number patterns. Now, I truly love number patterns because number patterns allows you to find a relationship between consecutive terms that's obviously repeating, and you then get to describe it using mathematical formulae. So it helps you understand things happening with numbers on a different level. Another reason why I love it is because we could view patterns in real life. Okay, and so there's numerous ways in which we can see real life applications with what we describe here. Have you heard of the Fibonacci sequence? So maybe at upcoming lessons where we do extra things well, I think what I could tell you about is that going forward, we're going to be hosting or launching a new series on the NITheCS channel. And in one of those series, I'm going to be calling that series Math Tales. So I'm just digressing a bit. But I guess in Math Tales, I'll tell you a tale about the Fibonacci sequence. So that's something to look forward to. All right, so Math Tales is an upcoming series that's going to be on the NITheCS channel. But now let's go back to number patterns. Okay, so in number patterns, this section in particular, right, so I'm going to ask a question and I want to try and see what responses we get. There were 3 different types of patterns that you had encountered in school, isn't that so? So can you name them for me? Let me look at the chat box. What's the first answer that's going to be appearing? Arithmetic, brilliant. Thank you for that. The second answer I see is geometric, and the third, I definitely spotted it, but it's now moving quite fast. Quadratic. So thank you everyone for those responses. That is precisely what I was looking for. So we're going to be recapping on arithmetic patterns, geometric patterns, and quadratic patterns. All right, so what I'm going to kick us off with is actually quadratic patterns, right? So quadratic number patterns have a specific general formula, right? So let's talk all things quadratic. Okay, so the general term for any number pattern, by a number pattern, I simply mean a sequence of numbers, right? So it could be A, comma B, comma C, comma D, continuing indefinitely. And so right now, we're going to talk about what happens if A, B, C, D continuing indefinitely. These numbers that follow the sequence is actually quadratic in nature. What does it mean? So this number pattern would be called quadratic if its general term, which you denote in school as Tn, has the following representation. Tn equals to a n squared plus bn plus c. And in particular, n is an element of the naturals. Okay, wonderful. So maybe it is now better for me to use your notation and replace it in the following way, that we have term T1, term T2, term 3, T3, 4, T5, and so on. So we have the sequence. All right, so the question is now, given a number pattern, how am I able to determine its general formula? The question is, what is A? What is B? And what is C? Okay, so that's what we want to quickly explore, so that faced with a number pattern, if we identify it as quadratic, we would then be able to characterize A, B, and C. Now, a quadratic number pattern has the following form. So that's the first criteria, 1. And the second thing that I could tell you about a quadratic number pattern is 2, that it is a number pattern that has a second common difference. Isn't that so? Or I should say the words rather, has a common second difference, meaning that the second difference of consecutive pairs. So we'll go through this exercise of finding out what the second difference means is exactly the same number when I say common. That's what I mean when I say common. Okay, so by a second difference, let's just do this. Let's say I gave you the pattern. Okay, let's work with 72, 100, 120, and let's go with 132. Right, so this is, it turns out that what I've written down here is a quadratic number pattern. So if it is indeed so, then we must be able to find a common second difference. So what is the first difference? By a first difference, I simply mean that we're going to be taking the difference between consecutive values in the sequence. So I will have to take 100 minus 72. And what is 100 minus 72? That value is 28. Okay, I see there are some stuff in the chat box. Okay, someone did say that the audio is off and someone else offered some advice to log off and log back in again. Right, so what is the second difference between 120 and 100? That is simply 20. And the difference between 132 and 120 in here is simply the value of 12. So this is the first difference, right? So that's important. This sequence that I've now generated, observe that we've actually generated a new sequence, haven't we? This is called the first difference. So we are interested in the second difference. So let's go for it. Let's complete this procedure one more time. So if I do this one more time, what is 20 minus 28? The answer is -8. What is 12 minus 20? And observe that again, the answer is -8. So in this situation, we now observe that the second difference is indeed common. And whenever you're given a number pattern, a sequence of numbers, and if you generate the first difference and then you generate the second difference and you see that the second difference is common, then that number pattern is quadratic in nature. And in particular, it would be expressed by that general term. So again, it comes down to the question that we've written down here. How do I determine A, B, and C? Because if I find those values, then I could write down the general term for any quadratic sequence. All right, so let's go through a derivation. Right, so we're going to go through this together. So we have that Tn is characterized by an squared plus bn plus c. So what I want to do is I want to now get a description of the first term, the second term, the third term, and the fourth term. So let's do it. So if I want to find out term 1, I simply have to replace n by the value 1. So I plug in 1. So let's do that. So if I substitute 1 into Tn, T1 equals to A plus B plus C. Does everybody follow what I've just done? I'm just waiting for some responses in the chat box. Are we all following? Is anybody lost? How are we doing? Yes to say that you're following. Okay, wonderful. Got some good responses. Right, so that's T1. So now that we understand what's happening, let's go ahead and compute T2. So now all we want to do is we want to replace n by 2 everywhere in that formula. So then it's a multiplied to 2 squared, which is 4a, plus b times n, but n is 2. So it's 2b plus c. Okay, let's do it again. Let's substitute in n equals to 3. So then I've got 3 squared. And so now if I'm putting in 3 squared, that's going to give me a value of 9. Right, so I put in a 3 there, and now I put in a 3 there, so I get 3b plus c. All right, wonderful. And then let's repeat it for T4. And so now I put 4 in there. So it's a times 4 squared. So that's 16a plus 4b plus c. Now you must be wondering, why on earth am I doing this? For a very good reason. Okay, so we are trying to determine what is a, b, and c. Okay, so now let's write down these terms. Let's compute the first difference and let's compute the second difference. Okay, so that's what I'm going to do. So I've got T1, T2, T3, and T4. My T1 is nothing but a plus b plus c. T2 is 4a plus 2b plus c. T3 is 9a plus 3b plus c. And T4 is 16a plus 4b plus c. We're now going to compute the first difference. Right, let's go for it. So what is the difference between these first two terms? What is T2 minus T1? So let's take the a's. Let's take 4a and subtract a. I get 3a. 2b minus b. I get positive b. And c minus c. Well, that's just 0, so I add a 0. So observe that the first difference here between these two terms is 3a plus b. We can repeat the procedure. So then I get 9a minus 4a, and that's 5a plus b. Okay, so I've done the difference again for the terms containing b and the terms containing c. And then I repeat here, 16a minus 9a. And so what is 16 minus 9? That gives me 7a, again, plus b. 4b minus 3b is b. So that's our first difference. I hope everybody is doing well up until this point. I'm just checking the chat box. Okay, I think everything seems good. So now we're going on to determine the second difference, right? So I'm going to make a note. This was the first difference. And now we're going to talk about the second difference. Right, so what is the second difference? Take the second term and subtract the first. 5a minus 3a is 2a. b minus b is 0. It's just 2a. Right, so then I've got 7a plus b minus 5a plus b, and I've got 2a. Observe that again, in this general way, what has happened? The second difference is indeed common, isn't that so? And what is the representation of the second difference? It is 2 times a. Okay. And then there's one more important thing. So let's talk about that before we move on. Okay, so I need a highlighter. Observe that the first term in the sequence for the for the first difference is 3a plus b, and the first term in the sequence is represented by a plus b plus c. So we now have 3 equations that we could use that could help us determine what is the value of a, what is the value of b, and what is the value of c. So how would I go about doing that? I would take the number that I have in the second difference. So the second difference is now equal to 2a. We then have that the first term in the first difference sequence, because this itself is a sequence on its own, that is 3a plus b. So that's one important thing. So I'm writing down the conclusions that we've got from this exercise. Okay, and then we observe that T1, the first term in the quadratic sequence that you started off with, is represented by a plus B plus C. And utilizing this, we could now obtain the second difference, equate it to 2a, and solve for a. Then plug a into the first term for the first difference and obtain and solve for b. And then take a and b, plug it into a plus b plus c, and solve for c when it's equated to the first term in the sequence. Is everybody following up to that point? Okay, I see we have a question. Someone asked, our first year is going to have their own section, session. Okay, so that's a good suggestion. That's something we can consider. So I'm glad everybody's following. We've got a resounding yes. Okay, wonderful. So now that we understand this, that means that the first question that I posed, can we solve for A, B, and C? The answer to this is yes, based on everything that I had just explained. So let's go ahead and let's look at a question from last year's exam. Right, so this is question 2 from the June-July exam that appeared in paper 1. And so I thought it would be a good exercise to look at something that you would actually receive or be tested on. So question 2.1. Right, so we're given a quadratic sequence. You're told it's a quadratic sequence. So immediately you should know, well, what does that mean? It means that there's a common second difference, okay? And what else does it mean? It means that its general term will be expressed in the form an squared plus bn plus c. That's what it means, okay? And so the first question is determine Tn. So that's great. So let's go ahead and do that. So we're looking at question 2.1.1. Okay, so we need to find Tn, which means we need to find A, B, and C. That's essentially what this question boils down to. Okay, so technically we have already encountered this sequence because I deliberately had provided it to us right here. And so we have already done some of the key work. So look at this. We have already computed the first difference, and we also already put in the effort to compute the second difference. So we know that the second difference is -8. And what did we just learn through our derivation? We had seen that the second difference is equal to 2a. Our second difference in this case was -8. So let's solve. I can just write that down. -8, which was the second difference, equals to 2a. And so what does that then imply? That implies that therefore a equals to -4. Does everybody understand what I have done here? Wonderful. I see someone had already put the answer in that a is -4. Okay, we do have someone that says no. So let's see if I could change that no into a yes. All right. So to whoever wants to answer no, we've started off with a sequence 72, 100, 120, and 132. We are told that it's quadratic in nature. Because it's quadratic, its general term has that form as I had explained. And if we had to compute the second difference, its second difference would be -8. How did we follow the procedure to get there? First off, we computed the first difference. Okay, this is what we did. We computed the first difference. How do you get the difference? You simply take consecutive numbers and you subtract the second. So you subtract the first from the second term. So in this case, it was 100 minus 72, giving me 28. Then it was 120 minus 100, giving me 20. And I repeated that procedure. So on the second level, the middle level that you're looking at, that I've highlighted in yellow, that's the first difference. We then go one level below. We go one step down again, and we compute the difference again. So I take the second value in this yellow sequence, and I subtract the first value from it. So 20 minus 28 gives me -8. 12 minus 20 gives me -8. And that's the second difference. It's common. Later on, we then went on to this derivation where we had seen that if your sequence is quadratic, then the common difference is represented by 2a. And so that's what I wrote down. I said that, well, -8 is now equal to 2a. So to the person that said no, do you now understand what we've done? I hope you do, okay? So I'm now moving on. I hope that cleared any confusion that you might have had. Okay, so where were we? Right, so we were answering this question. So we now know that a equals to -4. What else do we know from our earlier derivation? We had seen here that the first term in the first difference sequence is equal to 3a plus b. Okay, so I know that 3a plus b equals to the first term in the first difference sequence. And what was that value? That value was 28. So to put things into perspective, this is what is happening. The second difference is equal to 2a. The first term in the first difference sequence is equal to 3a plus b. This is what we had seen. I'm not making this up, we derived it. And the first value in the quadratic sequence has the form a plus b plus c. So all I'm doing is I'm equating it. We're going to solve 3a plus b equals to 28 and a plus b plus c equals to 72. Everybody follows that? Okay, wonderful. And I see we've got a response from the person who originally answered no, and that has changed to a yes, so I'm quite excited about that. Okay, so now let's go back. So we've all agreed on what I said we're going to do, and we're now going to equate 3a plus b to, 28. And now we're going to solve for b, because a is known, right? So it's 3 times -4 plus b equals to 28. And so now I can solve for b. So that means b equals to, so 3 times -4 is -12. And then I can add 12 to both sides of the equation. So if I do that, then I see that b equals to +40. And so we now have the value for b. All right, so let's repeat. We've got one more step to complete before we're done here. Right, so now we have to deal with the first term in the quadratic sequence, right? And so that term 72 we have seen is equal to a plus b plus c. Right, so let's go back and do that. So we see that a plus b plus c equals to 72. But we know what a is and we know what b is. A is -4. B is 40. C is unknown, and we are currently going to solve for it. Okay, so on the left-hand side, I've got 40 minus 4, which is 36. Okay, and so what I can then do is I observe that C is then equal to 72 minus 36. And what is 72 minus 36? It's actually 36. So we've now found A, B, and C. All right, so let's look at this. Now that I've got all of the values, there they are here. A is -4, B is 40, and C is +36. That means I can write down the general term. What is the general term? It is nothing but an squared plus bn plus c. We've seen that a is -4, b is 40, and c is 36. So Tn is equal to this formula. Wonderful. So this is what we now have, and I hope that everyone has understood this procedure and understood the derivation. Okay, so I'm glad that everyone's participating in the chat box. I'm really happy with that. Let me take a look at the Q&A. Okay, so I think I've already answered this. So that was done. Okay, so that is what I wanted to tell you about quadratic sequences. Let's talk about something else. Let's now go on to talk about something that maybe you might find a little bit more simpler, and that is arithmetic sequences, okay? So who wants to tell me what is an arithmetic sequence? You can type it in the chat box. Right, so we're looking at arithmetic. In summary, just in like a sentence, let's look at what the responses are. Okay, and so we have some lovely responses. And so that is that the first difference is common. Wonderful. So if you have a sequence of terms, right? So if you've got your T1, your T2, T3, right? And if you observe the following, right? If you observe that the first difference, meaning T2 minus T1, is equal to, let's do the next one, rather, I think a different color is needed. Let me just shift this a little. Okay, so, and if we take the difference again for the next consecutive pair, so if I talk about T3 minus T2, right? So if we compute these things, right? So of course, this is the first difference. This is what we were doing in the quadratic sequence, right? We computed the first difference, then we computed the second difference. So if it turns out that when we continue computing these differences, the first difference, if it turns out that those values are equal, then in this situation, the sequence is called an arithmetic sequence. So thank you to those of you who answered in the chat box and explained already that an arithmetic sequence is a sequence that has a common difference. So that is indeed the case. And so we call this common difference D. Okay, so that's what's happening. So given a particular sequence of terms, so I'm keeping a general T2, that is T3, T4, T5, just going on, we see that the difference between consecutive numbers is simply D. Okay, so we denote the common difference by D, and we also denote the first term by A. So that is going to be the convention that we set ourselves as we go forward. So look at what's actually happening. You start off with a number, and to get the next number, you would have to add D to it. Then to get the next number, you would have to add D again, and you continuously add D. Isn't that the case? So if I wanted a particular Tn, the general term, the term in the nth position, it simply means that I start off with the first term and I add, so if I'm looking at the nth position, it means I would be adding D n minus 1 times, isn't that so? So if I wanted T4, I will be adding D 3 times. Can you see it's 1 less than the term that I'm working with? Similarly, if I wanted to deal with T5, then I would add D 4 times to get to T5. Obviously, it's being added to the first term, A. So what is the pattern in here? What have we realized? How do I mathematically write down this relationship? It simply is written as follows, that it's the first term being added to n minus 1 multiples of d. It's one less than the term that you're looking for. Does everybody understand that bit? Okay. Wonderful. And so that is the general term. So perhaps let's look at an example, but I think what we could do is we could continue to look at this question here. Right, so let's go back to the examination. So the examination question 2.1.2 then tells you the following. It says that a term in the quadratic sequence, so we're still working with the original sequence we already worked with, is equal to the 12th term, right? So, I mean, we usually call this your T12, right? Of the sequence of first differences. So here is our key word. We have to look at the first difference. Okay, so remember that I subtly hinted when we were dealing with quadratic sequences that when we were computing the second difference in this situation, when we were computing the first difference in this situation, this sequence itself was a number pattern, right? Because of course, do you all agree with me that if I regard (28, 20, 12) and that sequence continues as a sequence, then this would be a arithmetic sequence? Does everybody see that? Why is that the case? Because 28, 20, 12 continuing has a common first difference. Isn't that so? All right, so we see that this sequence, that our first difference, if we look at it on its own, it has its own first difference, which is common, and therefore that 28, 20, and 12 continuing in that particular pattern is itself an arithmetic pattern, which is what we were currently discussing. All right, so going back to the question, I mean, we haven't finished reading it. It says that this sequence is equal to the 12th term. So a term in this quadratic sequence, is equal to the 12th term of the sequence of first differences. Okay, so I think we all understand what that now means because I went back and we looked at the first differences. And it says determine the position of this term in the quadratic sequence. Okay, wonderful. So some term in the quadratic sequence is equal to T12 in this arithmetic sequence. That's what's happened. All right. So let's write down that arithmetic sequence. So again, we just need to remember that that sequence was 28, 20, and 12. Let's write it down. This was question 2.1.2, if I'm not mistaken. And we've got that the first difference sequence is given by 28, 20. What is the last term? Was it 12, right? Yes, it was 12. And 12. We had seen that it had a common difference of -8. So because it has a common difference, clearly we can write down a general term for this sequence, isn't that so? And here's the formula that I've already discussed. So what does the general term for this equal to? So let's denote the general term of the above sequence by let's call it Kn. So the only reason I'm doing this, I'm not using Tn, is because, well, technically, Tn is already used up because we've already used Tn to denote the general term for the quadratic sequence. Okay, so that means we don't want T12, we are considering K12. Does everybody understand this change in notation? I hope it's not confusing you, but I need to denote it differently because Tn is already describing the quadratic sequence, and now we're dealing with an arithmetic sequence. Okay, someone said they didn't understand this. Okay, I'll explain it again. Right. So, of course, based on what you've learned in school, Tn denotes the general term, right? But now we're working with two sequences, so I can't let Tn represent the general term for both sequences, right? So Tn will denote the general term for the quadratic sequence, and I'm going to say that Kn denotes the general term for the arithmetic sequence. That's all. It's just notation. Okay, so that's what we're doing. We already have the formula for Tn. The formula for Tn is minus 4n squared plus 40n plus 36. So right now we need the general term for the arithmetic sequence 28, 20, 12, and it's continuing. So what is Kn? So what is the general formula for an arithmetic sequence? Clearly this is arithmetic because it has a common difference. It is a plus n minus 1 into d. Okay, what is the first term? The first term is 28. Then we've got n minus 1. What is the common difference? The common difference is negative 8. So let's simplify. So therefore, the general term, Kn, is 28 minus 8n plus 8. And so I can simplify. So therefore, Kn equals to 28 plus 8, giving me a value of 36 minus 8n. Okay, so I hope that everyone is following this. Does everyone understand what's happened? Okay, wonderful. So someone's already told me Kn equals 36 minus 8n, so I'm glad you're following. Right, so we now know that the general term in this arithmetic series, arithmetic pattern, has the form or has a general term formula 36 minus 8n. So we need the 12th term. We were told that some term in the quadratic sequence is equal to the 12th term here. So now we need to find out, well, what is k of 12? That's what I need to know. 36 minus 8 times 12. And what is the answer that you get here? Okay, I'm seeing responses. Right, so I think everybody's now understood. So I'm really glad that you're all following. Okay, so the answer that we're getting, so this is 36 minus 96, and so we're getting negative 60. Isn't that so? Is that what you get when you do the check on your end? Wonderful. Right, so thank you for participating there. So now we know that the 12th term in this arithmetic sequence is minus 60, and it turns out, according to the question, let's go back to that question, that some term in the quadratic sequence is equal to K12. So now we need to find which term it is, meaning we're solving for n. So let's solve for n. So remember, what we need is this formula. I need to remember it. Let me write it down so I can write it down again. What is this? Minus 4n squared plus 40n plus 36. Okay, I'll write it down on the next page. Right. So we have that Tn equals to, I wrote this down, minus 4n squared plus 40n plus 36. I hope I've copied it down correctly. Let's double check. Yes, so that is indeed what I've written down. And we need to find n when Tn here equals to negative 60. Does everybody understand that this is what we needed to solve, right? So now let's solve that. So that means we're now equating negative 4n squared plus 40n plus 36 equals to negative 60, right? And so solving this in here, that tells me that negative 4n squared plus 40n, and now I'm going to add 60 to both sides, plus 96 equals to 0. Okay, I hope everybody is following. Then I'm going to divide throughout by negative 4. So then I get n squared. Okay, this is if I divide by negative 4. Minus 10n minus 24 equals to 0. Right, so I hope that you're all on board with what's happened there. And then we can factorize this. Remember, we're solving for n, so let's factorize. So I write down 2 factors, and I then see that the first one is going to be, let's go negative 12, and the next one would be plus 2. Everybody following that? Looking at our chat box. Okay, we have some no's. Okay, so where exactly is the misunderstanding arising? So let's go back to the question. The question said that a term in the quadratic sequence is equal to the 12th term in the first different sequence, right? In the first different sequence. So there is some term here, there's some Tn in here in the green sequence, such that Tn is equal to K12. So Tn, in our case, that K12 is equal to negative 60. And so that's what we needed to solve, because we found out that K12 was negative 60. But we know what Tn is. We did all of the work. Here's Tn. Tn is minus 4n squared plus 40n plus 36. And so we say Tn must then be equated to negative 60. And we've solved. And this is where we have arrived at. So those of you that said no, are we now on board? Yes, someone asked, why do we sub into the Tn equation? And I just explained that. So I hope that that's answered it. Right, so we see that Tn needed to be equated to K12. That meant that Tn must be equal to minus 60. And this is what Tn is. It's equal to minus 60. And now we're solving for n. So then we see this implies that n equals to positive 12 or n equals to negative 2. We reject this option because n can only be a natural number, and we accept, therefore, that it is the 12th term in the quadratic sequence. So it's T12 that equals to K, what is it? T12 equals to K12. Right, so I hope that that has now clarified it. Wonderful. So someone's answered yes. Okay, so that was us answering the question here that dealt with quadratic sequences, as well as an application using arithmetic sequences. So that was quite an exciting question. It was double fold. It tested you on a different way by combining 2 different types of sequences in one question. So I found that very interesting. Right, and going back in here. So that is what we have learned based on arithmetic sequences. But that's not all that you're supposed to know, isn't that? So there's a lot more that you were supposed to know. Of course, I'm limited by time and this 1 hour duration, so I can't teach you everything. But what I could remind you is that you also need to remember your sum to n terms formula. Right, so when you're dealing with arithmetic sequences, there's also the sum to n terms. Right, so when you are summing the terms, in a sequence, we refer to this as a series. So that is why typically when you come across the topic, they say sequences and series, because they're testing you not just on general terms for number patterns, but also on sum to n terms. Okay, and so the sum to n terms formula is actually provided to you in your information sheet. So I've put up the information sheet in here, right? So this is it. Whenever you write an exam, you are given the same sheet. Let's quickly take a look at which pieces of information in here is applicable to number patterns and that which we are studying today. So observe that here we have Tn. The general term expresses a plus n minus 1 times d. And then here we've got sum to n terms. So this bit in here, this is dealing with arithmetic sequences, right? In the line below, I'll change the color, right? So we haven't discussed this bit yet, but this general term is the general term that is utilized when dealing with geometric series and sequences, right? So geometric sequences. So that is geometric. And here, let's look a bit closely. So I'm not going to have time to go through this. I did plan to do so though. This was a sum to n terms formula for a geometric sequence. And then there's a sum to infinity. And this is a fantastic formula, because it tells you if you have a sequence that's continuing indefinitely, satisfying the property that there's a common ratio, because that's what geometric means, then if that sequence converges, right? So if for some n value, we find that as n tends to infinity, that the sequence itself tends to converge to a single value, then we can compute something called the sum to infinity. And it turns out that that formula is so simple. It's a divided by 1 minus r. Okay, so for these things that I have not gotten an opportunity to cover, in particular, I have not gone through that. I have not gone through this, and I've not gone through this either. I'd like to refer you to videos that I've already created. So these videos are already found on my Dr. C Rathilal YouTube channel. So whatever I could not do today is already found there. In there, what I like about that is that you will find a derivation for this formula. Okay. And there is another video that deals specifically with geometric sequences and series. So unfortunately, I couldn't do that today. We're running out of time. So if you're required to recap on that, I'd like to refer you to those resources. And of course, there will be more resources rolling out on NITheCS upcoming channels, which we are going to be launching some really fun series on soon. Okay, so what I did plan to do was I planned to answer the following question with you thereafter that dealt with geometric sequences. So just to quickly give you a quick intro, if you've forgotten and you just need your recap, how do geometric sequences work, right? So you have your terms, T1, T2, T3, and so on. And you would observe that the relationship between consecutive terms in here is not a common difference, but rather a common ratio, okay? So it's a common ratio which we denote by R, and we still denote the first term by A, okay? So how do you get this ratio? It is the second term divided by the one that came before it, by T1, and likewise T3 divided by T2. So the common ratio is given by taking these pairs, these consecutive pairs, and taking the number on the right and dividing it by the number to the left of it. And so if you observe that the relationship amongst these terms is that they have a corresponding ratio, a common ratio, then we call that a geometric sequence. All right, and as you had seen in the formula sheet, the general term is given by A multiplied to R raised to the power n minus 1. And that, if you think about this logically, it truly makes sense, because what's actually happening in here? You take the first term and you multiply it by the ratio R to get T2. You then multiply T2 by R to get T3. And you continuously multiply by R to get the next term. So if you wanted Tn, you're simply taking the first term and multiplying it to R raised to the power n minus 1. So one less than the term that you're looking at. And so that question deals with asking you, well, what is the general term? You're given R and you get given A. So clearly you could write down the general formula. They ask you for T7. And then they ask you to which term in the series, meaning sum to n terms, is equal to 16 over 15,625. So utilizing that formula from your formula sheet, unfortunately, I don't have the time to go through this now. You could then find out which term you could solve for n. And so I think that is all that I have time for today. There's a lot of responses in the chat box. Let's see. So I just want to quickly see what else has been asked. Okay, so there's nothing much pertaining to this. Well, so I hope, everybody, that you have enjoyed this session, right? I truly enjoyed teaching you a little bit more in this limited time about number patterns. In particular, we focused a lot on quadratic sequences and arithmetic sequences, and I've given you some I've given you an idea of where to find other resources on geometric sequences that I haven't, unfortunately, gotten to today. So don't forget that we have an upcoming lesson next Friday, and in that lesson, I will be covering geometry. So I look forward to seeing you there, and thank you for joining us on this Friday evening. I'm so glad to see that so many of you are dedicated to your studies. All right, so take care, and I will see you soon.